So in the realm of molecular mechanics, this is the kind of force field that we use. Depending on the force field, depending on the school of thought that has designed the force field, they're more or less sophisticated. So what you have, like in the pink boxes, are the common denominators to all force fields. That you have the usual bond stretch, valence angle stretch, dihedral torsional potential. Then you have the non-bonded electrostatics and van der Waals. And then you have like this extra term that we use, which is called outer plane, or improper, to maintain a central pattern in the plane of the three surrounding ones. Then some force field, especially force field used by that you find like a commercial force field, like the force field from Axelrod, CBFF, CFF, the force field of Tom Halgren. They include coupling terms. So, for instance, if you do a quantum chemical calculation and you for a water molecule and you play with the valence angle, so when you open the valence angle, you shorten the bond length. So this is taken into account by this coupling. Okay. So in an equation, this is the kind of functional that you're using. So this is the Amber force field. Recognize here Peter Coleman. As I was mentioning yesterday to some, in the Amber force field, we distinguish between non-bonded terms involving exactly 3 bonds, 3 chemical bonds. This is called 1,4, and non-bonded terms that involve more bonds, or that actually are involve like intermolecular interactions. But for intramolecular interactions, we do not count 1, 2, 1, 3. We only start counting at 1,4. And the 1/4 are weighted down. So in the Amber force field, the electrostatic is divided by 2, multiplied by 0.5. The van der Waals is multiplied by 0.5. The electrostatic is multiplied by 0.83. This is to reflect the fact that the torsional potential already accounts for van der Waals and electrostatics interaction. So another common trait of academic force fields, macromolecular force fields, is they rest on the hypothesis that parameters are transferable. So if you have a CH3, a methyl group, in an aliphatic compound, or an alcohol, or a peptide, you basically use the same parameters, notwithstanding the fact that the chemical environment is slightly different. And so a consequence of that is that you're using or you're resorting to a limited number of atom types. Depending on the force field, you'll have more or less atom types. The charm force field is pretty greedy in terms of the number of distinct atom types. OPLS, on the contrary, is pretty rich. All these macromolecular force fields, they rely on harmonic approximation of bond stretching. Of course, this is not ideal. So this would be a quantum mechanical potential for the stretching of ethane, and so this would be in green the approximation that we use. Let me jump directly to what was actually the question that you were asking. So you know, of course, how torsional potentials work. Yes. So we use a Fourier series and we just add terms. Everybody's familiar with that? Okay. So that's good.
It's easy for a browse, actually.
Pardon me?
people looked like they were confused by that. Is that no?
It's clear for everybody. I mean, you know how torsional potentials are built or not. If it's not clear, just raise your hand. Okay, so that's good. So now the real question was, what about electrostatic interactions and van der Waals interactions? What distinguishes the charm force field from the Amber force field? So in the end, so those are like two distinct philosophies. So the Peter Coleman philosophy is the electrostatic potential is the fingerprint of the molecule. Therefore, if we're able to reproduce this fingerprint properly, then in principle we should be able to reproduce electrostatic interactions in an intermolecular sense. Okay? And so what the approach is based on is a mapping of the electrostatic potential around the molecule of interest that you want to parameterize. So the way you do it, I'm going to show you in a minute. You use a grid of points, and you calculate a reference quantum mechanical potential. We're going to fit this potential with a series of charge, which is at variance or in stark contrast with the charm philosophy, which relies on intermolecular interactions. And so in the charm approach, we use water molecules that we place randomly around the molecule. And so we calculate for each relative position of the water molecule around the solute of interest, the solute that we want to parameterize. We calculate quantum mechanically the interaction energy of that water molecule with the molecule of interest. Okay? So we repeat this calculation a number of times for different relative position of the probe water molecule. And then we fit charges so that in an average sense, they reproduce these interaction energies. Okay? So you see it's very different. I mean, the concept is very different. So returning to the Amber approach, the way we do it is so we have the molecule, we have the van der Waals envelope of the molecule, which is usually overestimated. The reason for that is you may remember that the electrostatic potential has two components. It has a short-range component, which is due to the penetration of the electron clouds, and we don't want that to contaminate the long-range part, which is the exact, quote-unquote, exact multipolar part. We're going to describe this multipolar part by a truncation at the zeroth order, which is like, so when I say multipolar part, you can express the potential by a sum of charges term, dipole terms, quadrupole terms, and so on and so forth. We're going to just limit ourselves at the level of charges, which is almost like a heresy in the sense that, take for instance, sulfur. Sulfur has a very large local, atomic quadrupole. And we're going to try to reproduce this atomic quadrupole just using charges. Even the oxygen of water has a large quadrupole. So anyway, so the way we do that is, so we have this reference potential that we have mapped on a grid of points, usually a few thousand points. It doesn't cost anything. You know, once you have the wave function from the quantum mechanical calculation, calculating the electrostatic potential, which is the expected value of 1 over r, is just free. And so once you have the potential of a set of points, then you have to solve this system of equation. It's just like an overdetermined system of equation because you have way more points on the grid than you have unknowns, and the unknowns are the charges, the atomic charges. Okay. So this is what is done in Amber. There is one extra detail that I need to mention. So Peter Coleman, back in 1993, when he was reparameterizing the Amber force field, was concerned by the fact that charges are not conformationally independent. So you change the conformation of the molecule, and as a result, you change the chemical environment of the different atoms. Therefore, you modify the charge distribution, which is what you can call that intramolecular induction effects. It's a polarization effect, right? The local electric field felt by the different atoms vary as a function of the chemical environment. Ideally, you should treat that using explicit polarization terms. But we are in the realm of the pairwise additive approximation, and so of electrostatic or electronic distribution is fixed, right? So the trick that Peter Coleman used, and actually that actually goes to the group of Richards in England, is to introduce intramolecular induction effects in an average sense. So what they did is the following. So they considered for each molecule that they parameterized different conformations. Okay, and they calculated for this different conformation their respective Boltzmann weights. So for each conformation, they calculated the electrostatic potential on the grid point. And so they did like a multi-reference fit, but weighted down by the Boltzmann weight. So in an average sense, so the charges that you get are not really representative of any of these different conformations, but they do represent, they kind of take into account the induction effects in an average sense. Another thing that the Amber force field was notorious for, but the charm force field as well, is that back in those days, when they parameterized the force field, quantum chemical calculations were pretty expensive, and to take into account this time not the intramolecular induction effects, but the intermolecular induction effects, they used one of the deficiency of a famous Popel wave function or a basis set, 631G star, which tends to overestimate the polarity of the molecules. Now, why did it do that? Think about water molecules. Take water molecule in the gas phase, an isolated water molecule. Can someone remember what's the dipole moment of water molecule in the gas phase? Yes, yeah.
Isn't it just equidistant from each of the hydrogen atoms, just straight down?
Yeah, that's correct. I mean, but what's the value in the line?
78 or 80, something like that.
Oh, no. 1.6 divide. It's 1.6 divide. And now, if you measure the dipole moments of water in ice, basically in a condensed phase, you go up to 2.4 divide. So what happened in the meantime? I mean, when you go from the gaseous to the condensed phase, well, you have induction effects. So you have what's happening is that you take one isolated water molecule. That isolated water molecule feels the electric field. Well, first, it polarizes its environment, and then you have a reaction field. So the surrounding water molecule will polarize back that water molecule. So that extra polarization creates what we call an induced dipole moment, which is like a linear response theory. That induced dipole moment is proportional to the electric field felt by that water molecule, and the factor, the proportionality factor is the polarizability tensor. So the polarizability tensor, you can see that as the ability of the molecule to deform its electron cloud in response to an external electric field. So that induced dipole moment is about 0.7, 0.8 divide, which adds up to the static dipole moment, which is the dipole moment in the gas phase. So to compensate from the fact that all these charges are fitted from gas phase quantum mechanical calculation, and therefore should reflect the gas phase dipole moment. But knowing that these charges would be used in the context of condensed phase simulations, well, it was great to use, to take advantage of the deficiency of the 631G star basis set. But they were kind of shooting in the dark because, that basis set, well, it's notorious for overshooting the dipole moment, overshooting the polarity. But we don't really know, by how much it overshoots it, and it's molecule dependent. But it did a pretty good job, and that's what they used for water models and basically most of the parametrization. When it comes to the van der Waals interactions, they all rely on the same formulation. They try to describe the van der Waals potential by a very simplistic description, namely a Lennard-Jones 6-12 potential. And that was back in those days where it was very expensive to compute exponentials. They could have used the Buckingham potential, which is exponential 6. So the 6th term always makes sense. This is what you expect from dispersion. The fluctuation of the dipole moment is a 6th term. But the 12th term is something completely ad hoc. It's just like the square of the 6th term, right? Which was much cheaper to compute than the exponential term in the Buckingham potential. But strictly speaking, your repulsion term should not be a 12th term, but should be an exponential term. So, let me go to the flow chart. So this is the way force field, the Trump force field is parameterized. So this is quantum coppers. This is Alec Mackerel. So you always start with the bonded terms. So you do this gas phase calculation, or you take data from, in the old days they would just use that data from experiments. Then you do the electrostatic terms, and I showed you how to do it. So you place a water molecule randomly. Incidentally, the charges, if you look at the library of amino acids, charm force field, in the topology file, and if you look at the charges in the amber force field, you'll see that they're very different. The charm force field, much bigger, which tells you that you should not, mix force fields. So, if you're trying to parameterize or want to simulate something and you don't have the parameters, you're using the charm force, you don't have the parameters, but hey, some guy did a parameterization for the amber force field. Let's use those charges. No, you can't do that. The force field is a very fragile, very subtle construction, and it relies on a load of approximation. And so you cannot just take parameters that were obtained with one philosophy. And it's kind of a whole philosophy, right? It's so you cannot just take whatever elements that you need and transfer them to another force field. You need to, if you want to be kosher, you need to follow the same philosophy if you want to be parameterized. So then, the way they determine the van der Waals force field, the van der Waals term, they use liquid simulation. But that's kind of a common trait to most force fielding. The amber people were doing the same. The OPLS people were doing the same. And then finally, as I said yesterday, quoting Benoit Roux, if this is the antechamber of the garbage yard, this is the garbage yard. So the torsional term is is basically the final term that you adjust to kind of reconcile everything. Keep in mind that in the force field, you're making a lot of approximation. I mean, at every step of the way, you're making an approximation. At the bottom term, you're making a harmonic approximation. So you're basically neglecting all the anomalisticity terms. You're neglecting all the coupling terms. You know, when one bond vibrates, it kind of feels the neighboring vibration, but you ignore that. Here, your approximation is you're truncating at the 0th order. Okay, so you're forgetting an important component of the charge distribution, especially when you have atoms that involve large local multiple moments. Here, well, you're replacing an exponential term by an r to the minus 12 term. Okay. And so basically, in the torsional term, that's where you will adjust everything to match. So in the amber force field, when they were parametrizing, one of the targets was the alanine dipeptide and glycine dipeptide. So they had like this very expensive scans, quantum mechanical scans, you know, getting the full torsional potential of diameter. They were trying to reproduce these maps as precisely as possible. And then I remember that in 1997, Rich Friesner came with this very expensive MP2 or local MP2 calculation of an alanine tetrapeptide. And the amber force field was not doing great. And by comparison, overshooting or over-stabilizing the alpha helical state. It was like a big drama because, you know, parametrization based on a dipeptide obviously was not sufficient. And the drama became even more acute when they tried to reparameterize the force field to match Friesner's data, but at the same time destroying the agreement for the alanine dipeptide. So it's really, it's you know, parametrization of force field is a big challenge. And I'm not even mentioning when you add polarizability. So it's tough. So what do you do when you're missing parameters? So if you're using the charm force field, there are a number of options that you can use. So you can utilize servers like CGNFF, ParamCam, basically to feed the PDB file of your the molecule for which you are seeking parameters that are not available in the library of parameters, and that server will do an atom typing to try to recognize the types of atoms and do an educated guess based on kind of knowledge-based educated guess. Now you have like more precise approaches like GAMP, which is developed by the Brew Group at the University of Chicago, and that does that kind of follows the previous flowchart and doing all the necessary quantum mechanical calculations to get you the missing parameters. You also have, in the same spirit as GAMP, you have developed here in this group, you have FFTK, which is a plugin of VMD, which you can use also to get the missing parameters. Because you can kind of take a different philosophy and maybe use a force field that is more adapted to the need, but then you need to change the force field altogether. This is the OPLS force field. It's Bill Jorgensen and Julian Tirado Rivas, who was like in charge of the parameterization of the OPLS force field. Bill Jorgensen is by training an organic chemist, and I think that this force field is notorious for being like probably the best force field or the best minimalist force field to describe organic species and organic compounds. He has spent, I mean, kind of, you know, in great work, not always recognized, but he has spent good chunk of this period of optimizing potential energy function. The new guys are using every day the work of Bill Jorgensen. When you're simulating with tip 3P water, tip 4P water, tip 5P water, or if you're using the OPLS force field, this is the work of Bill Jorgensen. And so this is a pretty complex force field, and it has like many, many, many terms. And for one atom type, you have many atom subtypes. So depending on, we have like, for instance, Ca is for aromatic carbons. Depending on the environment of that atom. So it's the same Ca, but with different parameters. So I was mentioning ParamChem. So this is the server that emanates from the mackerel group. So this is for the charm aficionados. So if you have a molecule that you need to parameterize, you can use that. It's an automated tool. It just like gives you back, send you back the parameters that you need. With so because it's knowledge based and kind of educated guesses, it returns the result with a flag, kind of a confidence index. So if it's uncertain about some parameters, it will tell you that it's kind of risky to use that. I think I will stop here. Did it answer your question? I mean, did it answer your doubts about force field? Yes? It did. Okay. Any question? Yes?
What am I supposed to think about aromatic stacking?
Yes? I think we've worked actually back in '96 with Peter Coleman. We published a couple of papers on pi stacking with the Amber force field. It's not bad. I mean, a pairwise additive force field is not doing too bad, surprisingly. So for those who are not familiar with pi stacking or pi interactions in general, if you take benzene, for instance, what quantum chemistry predicts is the most stable structure will be a parallel displaced structure. Then it will be a T-shaped, which is essentially dominated by charge quadrupole interactions, and finally the less stable structure would be like the full stacking, where you have quadrupole repulsion, electrostatic repulsion, but compensated or partially compensated by strong dispersion interaction. So force fields, surprisingly, are not doing too bad. They're doing much better by comparison than for pi cation interactions, which are very important in biology, and that kind of way underestimated because those interactions involve induction effects, through space induction effects. So basically, the polarizing charge will interact with the pi electron cloud of the aromatic compound, and typically with the charm force field or with the Amber force field, we're undershooting the interaction energy by, if we take like benzene and ammonium. So ammonium is a model of lysine side chain. We're kind of undershooting by 4 or 5 kcal/mol, which is not negligible. So for that, turning to a polarizable force field like the charm force field with the fluid model wouldn't be a bad idea. But for pi, surprisingly, we're not doing too bad. It just also kind of reflects a um, one of the issues of the force field, be good everywhere. So if you take benzene, we're not doing too great when it comes to hydration-free energy of benzene. The hydration-free energy of benzene is something like minus 0.4. It's slightly negative, kind of bulky and hydrophobic, but you still have like dispersion interactions, favorable dispersion interaction that kind of stabilize it. And I think that the charm force field predicts something like 0.8 or 0.4, so we more than KT above experiment. So when it comes to predicting the hierarchy of the dimers, we're not doing too bad.
Why I asked was about small molecule.
Yeah.
So how much stock should I put into my calculations?
Yeah, when you look at protein structures and like proteins that are or protein complexes that involve a lot of pi-pi interaction, whether pi stacking or parallel display stacking or even T-shape, those interactions are usually fairly well reproduced.
I'm not sure that I totally agree with that.
Totally disagree?
Not totally, I disagree. I'm not sure I totally agree. There has been some debate as to whether or not the issue is a balance of these interactions. So while producing specific pi-pi interactions in the gas phase may be very good, when you combine it with a water model, you may get different results qualitatively.
That's true. Yes, I mean, there are these solvophobic interactions.
And no one knows the answer to that question. So
yes.
it's maybe.
I was merely, referring to trying to reproduce the gas phase, the quantum mechanical gas phase calculation, and for that we're not doing too bad. And also, in an environment kind of protected from water in a protein, we're not doing too bad either. Now, in the context of water, maybe it's not so clear.
The test case was unfolding of nucleic acids was generally very. They were not melting at 400 Kelvin.
Yeah, but nucleic acid is a different story altogether.
Yeah, and again, the jury, no one's agreed what the answer to this is, but one solution was to increase the strength of interaction with water.
It's not just about the base pairs. It's also about, the phosphates and the ions around the phosphates.
Yeah, so we're doing well, but there's room to improve, and no one really knows what will get us there.
Okay, so yes.
I have some question about we are talking about interactions. So I was wondering if there is some appropriate force field that predict the hydrophobic interaction of the proteins.
Hydrophobic. What you mean by hydrophobic? I mean, are we doing good in terms of hydrophobic? In general, I would say yes. I mean, if you look at, for instance, protein complexes that are formed, like membrane proteins that are formed by alpha helices, pretty hydrophobic alpha helices interacting with the bilayer. In general, we're doing pretty good. I mean, if you compare with what we simulate and compare with the crystallographic structure, we're not doing too bad, yes. And then there is a whole body of simulation, especially from the Chandler group, work hydrophobic effect at different scales, and force fields seem to also be, pretty. I mean, I'm talking about like macromolecular force field, academic force field. Seem to be doing pretty good for that. Okay.
What aspects do you think of the force field need to be improved before you get like a next generation practice?
So there are two actually So it's a good, very interesting question. We just had in June we had a CCAP meeting on energy calculation going beyond KD. So KD is a prediction of mining for energy. So going beyond KD means in the interest of the pharmaceutical industry, be able to predict K-ons and K-alpha grade constants, which is like eminently kinetic properties. So one of the big challenges for the next years is to be able to do as good for thermodynamics or for kinetics as well as thermodynamics. Because let's face it, if you take the TIP3P water model, it's not a bad model. I mean, if you look at densities and for energy of hydration, cohesion energy, entropy of vaporization, it's not bad. I mean, given how simplistic the force field is, it's not bad. Dynamically speaking, it's not so good. I mean, like diffusion constant, self-diffusion of water in T3P is double with respect to the experimental values. So there is a lot of room for improvement. So I think that would be one of the directions to go for the coming years. And of course, with the increase of computational power going towards polarizable force fields is also the way to go. But I mean, so far, it would be difficult for me to say, oh, this is the this is the panacea, and you should absolutely use a polarizable force field from no harm, because there hasn't been any compelling evidence that you should always, I mean, kind of a universal solution turn to polarizability. We're not quite there. I mean, we're on the way there, but we're not quite there. Notwithstanding the humongous amount of effort to investigate, because I mean, getting parameters for this force is just like horrendous, but it hasn't yet fulfilled its promises. I would say that polarizable force field should be reserved for like very specific. There is also a cost involved in using this force field. It's cheaper than it used to be. I mean, the Drude force field definitely is cheaper than the old Friesner approach with distributed polarizability. What you have, for instance, in amoeba, which is not true. It's like a multiple description of the polarizability, truncated at the level of dipole polarizability, but still, it's the way it works is you kind of iterate over your polarizable sites until you have convergence of the induced dipole moment. Only then you calculate your interaction energy. So you have all this loop. So even if you use the induced dipole moment from the previous study as an initial guess, you still have to go through this loop, like using a Gauss-Seidel iteration scheme, and that kind of adds up quite a bit to the cost of the calculation. So now, even though you have access to these big machines like Titan or Blue Waters, you still have to make a choice. What do you want? Sample more, or sample less, but be more accurate. And sometimes sample less, trying to be more accurate, doesn't give you necessarily a better answer. I mean, the pairwise additive force fields that are available out there on the market are doing a pretty good job. I mean, for most of the stuff that we are interested in biophysics or biological-oriented simulations. Yes?
Following your comment for the water model, like how much work it is to parameterize the charm amber force field using more sophisticated water models. Following, if we know their philosophy,
then it would be like, starting from scratch, and it would be enormous. It would be enormous because, I mean, think about it. I mean, all the amino, just at the level of of proteins, you have to reparameterize all the amino acids, and so all the fragments, with different positions of the water molecule. Okay, now you get the new charges. But as I said, this is a subtle equilibrium, and in the flow chart to optimize the force field. Now, once you have a new charge distribution, then you need to reparameterize the Van der Waals parameters. And then you need to reparameterize the torsional potential. This is not something plug and play. You cannot just take one element and replace it by something that you think is a little bit better. Then you need to reparameterize everything downstream. Yes? My God, I mean, we're never going to start with transition path sampling today. Okay, so please.
So there are a couple versions of like charm or amber force field. So do you think the latest one is kind of always better than the previous one?
What's the latest one?
I mean,
The charm 36. The charm 36 is definitely an improvement over the previous, especially, I mean, here in the Schulten group, I mean, we do a lot of membrane protein simulations. Definitely for membrane, there has been like a major step forward in thanks to the effort of Jeff Clauda. Now we're getting some very good agreement with experiment. We do like a pure membrane simulation compare with the available data from NMR, thinking about membrane width, thinking about surface area per lipid, thinking about all the parameters. And the agreement is pretty good for a huge variety of lipids. I mean, these guys, Pasteur, Clauda, they've done an amazing amount of work to get you a variety of lipids. Now you can simulate. I mean, we are at the stage of where we can simulate lipid mixtures with additives. So you can even. I know that some people are already simulating mammalian membranes. I mean, of course, we're still simulating pure protein, POPC. We're still doing that, but we are at the stage where we have parameters for this more complex lipid, polyunsaturated lipids, single lipids, and different head groups. I mean, PC head groups, PG, PE, PS, and then there are sterols. So definitely improvement, yes.
do you have any suggestions that when we pick some force field, in general, we should go for the latest version or?
Well, latest is, I just gave you an example. I mean, with the Amber force field back in 1996, 1997, when they tried to, they did some backpedaling on the corner color force field in response to a data set of quantum mechanical calculations in a tetrapeptide, trying to reproduce the data of Friesner. They kind of destroyed the agreements that they had with the alanine dipeptide, the glycine dipeptide. And so there was this temporary force field, this temporary Amber force field, and then it went back to the corner force field. But to tell you the truth, I haven't really followed what was going on with the force field, the Amber force field lately. I know that there are multiple versions of it. I mean, in my group, I mean, also working on DNA, and Amber force field is still notorious to be a little bit superior to the charm force field for nucleic acids. But I think that we are using like 3 versions of the force field, which are like, they have like little subtleties. DNA and aDNA. I'm sorry. I mean, I'm not omniscience, and I'm not so. I haven't really followed the latest developments in the force field. I mean, I'm more like a charm person. Sorry. which is a shame, because I mean, I was a student of Peter Coleman. What can you do? Okay, can we start? Okay. So today it's kind of a continuation of what we talked about yesterday. So we're going to talk about reaction pathway and frenzy calculations using these reaction pathways. Let me give you an overview of what we're going to talk about this morning. So the first question is why. So why do we need reaction coordinates? Then what's a good reaction coordinate model? And I'm going to talk about one specific method. I mean, there is a variety of methods out there, but I'm going to focus on the string method. And then once I have the reaction path, once I have the minimum frenzy path, then I'm going to show you how you can calculate the frenzy change along this reaction pathway. And we'll show you a couple of applications. And finally, I'll say a few words about reconciling thermodynamics and kinetics. So the introduction is why do we need a reaction pathway, a reaction coordinate? So you remember that from yesterday's introduction. So those are like typical motions that we can see when we do applications in biophysics, and the time scales that are spanned by this different movements. So I was mentioning vibration, bond vibration, reorientation, correlation times that kind of span the picosecond time scale. The spontaneous binding of a drug to a protein, or in that case to an enzyme. It's more like the nanosecond to the microsecond time scale. Then protein folding, which can be as fast as the microsecond time scale. And finally, what Emma presented, this is here an ABC transporter, and those are like motions that span much longer time scale, typically millisecond to second time scale. So what we would like to be able to do, because we cannot afford to simulate over the millisecond time scale, let alone the second time scale. So we'd like to use energy calculations to capture these movements as efficiently and get the free energy associated to that as efficiently as possible. But as you've seen yesterday already with very simple system, very rapidly, I mean, your free energy calculation gets stuck. Even like for something as simple as dragging a methane molecule from the gas phase to the water phase. And because we were using a very naive reaction coordinate model, just the z direction, or the projection of the Euclidean distance separating the center of mass of methane from the center of mass of water to get to z. It's very, very naive. It's very intuitive, but it's also very naive. And what we see is that when you have like this very intricate transition between metastable states, usually they involve substantial collectivity, and this collectivity is difficult to capture with naive reaction coordinate models. And of course, they involve very rugged energy landscapes and the possibility to get trapped in a local minimum along this energy landscape. So what is a good reaction that's kind of relevant question. What's a good reaction coordinate model? So first, I would like to more like an homage to the work of David Chandler, who passed away this spring. David Chandler spent a lot of time in his career working on reaction coordinates and the concept of filter distribution. He was very adamant about using the correct vocabulary. So oftentimes, just like people use the word restraint when they mean constraint, or use the word constraint when they mean constraint, we often tend to use the word reaction coordinate, saying, "Oh, I've calculated the French calculation. I've calculated the energy change along this reaction coordinate." And how dare you use the word reaction coordinate? I mean, how do you know that this is the reaction coordinate? When in fact what you're using is a mere order parameter. The reaction coordinate, strictly speaking, should be living in R3n and should embrace a number of degrees of freedom. Let me illustrate this with this very simple example. Well, simple, sort of speaking simple. This is a synthetic channel formed by cyclic peptides. Each cyclic peptide contains 8 amino acids of alternated chirality. So DL, DL, DL. The result is that all the side chains are pointing outwards. Now, placed in a membrane, it will self-organize into this tubular structure. And the cohesion of this tubular structure is ensured by this anti-parallel, kind of beta anti-parallel arrangements with multiple hydrogen bonding between adjacent cyclic peptides. Now, through these cyclic peptides, you can have ions diffusing. Now, in this case, we have a chloride ion that is diffusing. And this chloride ion, as you can see, doesn't diffuse in a rectilinear fashion, but actually zigzags. And this is reflected here in this free energy landscape, where we actually consider 2 dimensions. Z is the long axis, and rho is the radial direction. Okay? And so you can see this hopping this, which is reflected here in the trajectory of the ion zigzagging in the channel. The reason why it's zigzagging is actually grazing, the ion is grazing the wall of the synthetic channel to meet NH groups and actually to chelate NH groups. Okay, so why does it do that? Well, chloride is pretty big. It doesn't go in the channel naked. It goes accompanied by water molecules. But in some portion, in some sections of the channel, it cannot move with all its water molecules. So it has to compensate this partial dehydration, transient dehydration, by chelation by the NH groups. Okay. Now, think about the reaction coordinate model in this context. The chelation to the NH group can be seen as a slow degree of freedom. Okay, so you have like the diffusion along the z-axis, and that diffusion along the z-axis is hampered by the chelation of the ion by the NH groups. Okay. So in this case, it's more advantageous to do a 2-dimensional, to take into account this chelation through the radial direction. So adding this extra degree of freedom in the free energy calculation. If you just have 1 degree of freedom, one distance as your reaction coordinate model, you'll be stuck And this will be mirrored, as some of you have seen yesterday, in their free energy calculations of methane diffusing across the water lamella, and seeing the sampling piling at one end of the window. You'll have the same thing here. Basically, your free energy method, your importance sampling algorithm, will help you in the z direction, but will not do anything to help you in the orthogonal degrees of freedom. You can see, for instance, think in terms of energetics, the chelation of a chloride ion by its NH group is pretty substantial, few kcal per mole. This few kcal per mole is a barrier. You can see that as a barrier in the orthogonal space. Okay? And whereas the importance sampling algorithm will help you along Z, it's stuck in the orthogonal space. Remember what I showed you yesterday with ABF. ABF, the expression of the average force, it's an ensemble average at constant psi. So in this case, if I'm only using Z as a direction, so it would be at constant Z. So it's an ensemble average, meaning that I have sampled all the other degrees of freedom. I've averaged over the other degrees of freedom. Okay? But if I'm stuck in the orthogonal manifold, then my ensemble average will be incomplete. Right? Therefore, very quickly, my free energy will be under or overestimated. Okay? So, going back to the reaction coordinates, so it defines the minimum, the true reaction coordinates define the minimum free energy pathway that connects a reference state to a target state. Okay? So in practice, I mean, our view is kind of naive view. We tend to coarse grain atomic detail, going from the Cartesian coordinate to the collective variable space. So in this case, I'm just using Z, that will be my collective variable space, a one-dimensional potential force. Possibly here, I'm improving dramatically the efficiency of the calculation by adding this extra degree of freedom, which would take care of chelation, dechelation. Okay? Incidentally, if you want to recover from this two-dimensional potential of the force, what's happening along Z, you just need to integrate over the other. So to summarize what I said before, in a pictorial manner, if I'm doing a free energy calculation with an important sampling algorithm like umbrella sampling, like ABF, alongside, so that method will help me to move in that direction. But because I have to deal with parallel valleys in the psi direction, and these parallel valleys are separated by high free energy barriers, and this high free energy barrier can be seen in this particular case as the energetic cost to rip off the ion from the NH group. Okay. So in that case, the importance sampling algorithm is not doing anything for me. And therefore, I'm lingering in the valley, hoping for the best, hoping that maybe at some stage I'll be able to cross the barrier and maybe go down and visit the other valley. So in this case, this is a very simplistic view, but it also tells you that using too small a window, that would be the case in umbrella sampling, would prevent the situation where you can go up the valley and then go down the other valley.
What? Sorry. If you're doing umbrella sampling, so you're doing umbrella sampling along your...
If I'm over-stratifying in psi, I may not be able to go up the hill and then go down. This particular example. Okay. So again, we have this stringent assumption when we do a one-dimensional potential of mean force. We average. This is particularly true when in the expression of ABF. We think that we are averaging all other fast and slow degrees of freedom, and that couldn't be further from the truth. So one of the good practices when you do free energy calculations, potential of mean force calculations, so you have no real clue a priori what are the relevant degrees of freedom. You just have you're just guided by your intuition. Case in point, methane translocating from water to water, from gas phase to water. So you're just using Z. Sounds reasonable. Good practice is to use the concept of committer. So the committer is the probability to reach the target state before you actually return to the reference state. So the transition state surface for the transition from A to B is formed of configuration where PB equals PA equals 1/2. But as you can see here, we have this two-dimensional free energy landscape with these two minima. And if you're considering the potential of mean force in the direction of Z1, okay, and we're shooting trajectories from this from the top of the potential of mean force, then we have an equal chance to go back from go back to A or go to B. Okay, and this translates in this kind of isocommitter form. So you have like this peak of the distribution of PA located at 1/2. So this is something that you should, as a good practice, always do. So when you submit a paper, when you have a free energy calculation with a potential of mean force, and especially if you're interested in doing some kinetics afterwards, you want to ascertain that the reaction coordinate model that you've used makes some sense. In this example here, this is the kind of a Muller potential. As you can see here, if I'm using Z1 as my reaction coordinate model and just Z1, and I'm shooting trajectories from the top of the potential of mean force from the barrier, then my committer distribution is all over the place. Definitely not peaked at 1/2. Definitely not Gaussian and peaked at 1/2. So that means that's symptomatic of a pathological choice of a reaction coordinate. So in this particular example, it was not a good idea to choose Z1 as my reaction coordinate model. I would have much better. It would have been much better to use Z1 and Z2 for that purpose. Yes.
Given a choice of a reaction coordinate model, will the fact that the autonomous piece is not properly sampled show up in the committer analysis? And
The committer, yeah.
Show up.
Yeah.
Basically, it's don't know that it's an incomplete reaction coordinate model or it's bad sampling.
Well, okay. So if you can have access to infinite sampling, in the end, you'll get the potential of mean force that you want. But it still remains that when it comes to the committer analysis, it will reveal that it was not the most clever, choice, and definitely this particular potential of mean force does not reflect the dynamics of the system for that particular variable. Am I making sense here? So let me go to the next slide. This is the key here, and that basically reflects what Abby was saying. The choice of the reaction coordinate model does not impact the thermodynamics, and that's by virtue of the fact that free energy is a state function. And its calculation doesn't depend, or the outcome of the calculation does not depend on the path that you have followed. Even if it's the craziest choice of a reaction coordinate model. By hook or by crook, you will get the delta delta G that you're seeking. It's going to be inefficient. The calculation will be inefficient, but with enough sampling, you'll get the answer. But you won't be able to do dynamics on that. And that's what Chandler was adamant about, like, claiming that you have the reaction coordinate. You can only claim that you have the reaction coordinate when you do this commuter analysis and show that PA, or the distribution of PA, is peaked at 0.5. So in this particular example, we have a potential mean force, and as a sanity check, we're placing ourselves at the top of the barrier, and we're shooting a bunch of trajectories. And what we see, so the top of the barrier is 0.49. What we see is that our commuter distribution is nicely peaked at 0.5. If we're slightly moving on the left-hand side, so we're here, so we're going at 0.469, and we see that the distribution of the commuter is completely shifted to the right. And likewise, when we go slightly on the right of the peak, about 0.51, we see that the commuter distribution completely shifted to the left. So when you can show this, if you just show me this and say, oh, sorry, yeah, that's my choice, good choice. And then you do all kinds of kinetic analysis, like rate constants, measurements, and so on. Yeah, maybe you're right, but please demonstrate me that your choice was a relevant one. And doing this, which is not super expensive, I mean, this multiple simulations that you're running from the top of the barrier are not that expensive. I mean, those are like short simulations. We just want to see the sampling falling on one side of the barrier or on the other side.
So just to clarify this, so what I'm doing on this commuter analysis is starting with a specific value of that zeta and then looking at the
Exactly. Yes, exactly. So I showed this slide yesterday I showed this slide yesterday. So, you're going to hear more from Giacomo. But basically, these are the basic components that you can, the basic collective variables that you can use in the Polarizable module to construct your reaction coordinate model. So, these variables in combination thereof. So let me illustrate very quickly, and then I answer your question. So take this example here, a very schematic model. This is a rotaxane. For those who are not familiar with what rotaxanes are, those are like molecular machines. It's a cyclodextrin that is threaded onto a molecular wire, and it has like end stations at the end. And usually it has like a highly polar charged group in the middle. So the cyclodextrin is either on the left side or on the right side. You can use that as a molecular switch. It's basically at the atomic level. This is like the primitive or rudimentary molecular switch. And the cyclodextrin can go on one side or on the other side under different kinds of stimuli. It can be temperature, it can be pH, depending on the chemical structure of the rotaxane. It can be it can drive the cyclodextrin on one side or on the other side. What I wanted to show you here is that oftentimes, you think about the rotaxane and just the cyclodextrin moving along the molecular thread. Well, it's not just a translational motion, it's also a rotational motion, and the two are coupled. And if you're trying to just simulate the translation of the cyclodextrin along the thread, then you're up for a lot of pain. And if you do the commuter analysis, you'll see very quickly that this was like a poor choice of the reaction coordinate model. So in this case, you really need to couple the translation and the rotational motion. Some of you yesterday worked on decaalanine. For the purpose of the tutorial, we limited ourselves in a range of the reaction coordinate model that is pretty safe. And from 12 to 32, you are basically you're going from the alpha helical state to a family of extended structure. It's pretty, in a matter of 5 nanoseconds, you nail down the potential of details, right? Now, if you're going below 12 angstrom, then you're visiting, now you're kind of getting lost in a haystack of more compact structures. And in terms of RMSD, you have like basically the same value of the RMSD, but you have like a huge degeneracy. I mean, you have a lot of, highly compact structures. And in this case, a simple Euclidean distance, end-to-end distance, is no longer able to discriminate between these different states. And what I want to show you here in this slide is really need, if you want to recover the alpha helical state, you really need to go to a higher dimensionality. So let me kind of summarize where we're standing so far. So we define a reaction coordinate model based on our chemical intuition, and this is our own good life. But then, if we want to do kinetics, especially if we want to do kinetics, we need to ascertain that the reaction coordinate model is a commuter function. And then, if it's not, what are the options? We can increase the dimensionality of the model, so this is what we're doing here, or that's what we're doing there. We can turn to ergodic sampling algorithms, and we're going to talk about that, by this basically exploit the parametrization schemes using replica, spawning clones of walkers to explore faster the various corners of the free energy landscape. Or search for a minimum action path. This is what we're going to talk about this morning.
So how would you do a similar testing for a multi-dimensional model? So like you see that one reaction coordinate has a sort of, so you decide, okay, I want to increase it to 2. How do you know that 2 is now going to be have a satisfying, or you don't think you go to 3 or higher?
So we tried to follow that strategy actually for methamphetamine back in 2010. So we went from 1 to 2 to 3. At some point you see with 2, you still have a kind of a coalescence of the minima of the basins, and so it's kind of pathological that there is something not quite right in our choice of collecting. So it was more like a trial and error.
Okay.
Yeah.
But there's not necessarily a formal analysis.
It was not a formal analysis. Okay. It was more like a heuristic approach to the problem.
Oh, thank you.
So now, I'm really late. So we have to go to.
You can probably rob 10 minutes for me if you want. Yeah. I don't think I'll fill the whole hour and a half.
It was like until 10:30, right?
Like 10:20, you can go. I believe that you can do 10:30.
10:30. I'll try to rush. No question, please. So let's talk about the string method very quickly. So, and this is Eric van den Eyden. So we will assume some minimum action path. So this is what we're after: minimum action path, a minimum free energy path, so this path will connect two basins, which you can see here, and so we consider the potential of mean force, of course, for this free energy landscape, and the potential mean force, I know that W of Z, and of course the force is related to the potential mean force to its gradient. And so what we're going to do is we're going to try to evolve this reaction, this minimum action path, such that df perp is equal to 0. So for those who are not familiar with this notation, by the way, D is the diffusion tensor. And for those who are not familiar with this notation, the perp notation, this is the orthogonal the orthogonal complement, such that V perp of V perp is equal to V. Okay, so this is very similar to. Let me show you. This is very similar to. I was supposed to show something here. Doesn't matter. It's very similar in spirit to what we do in steepest descents. With basically the direction, the search direction, is that of the gradient. So this is what we're doing in the basic string approach. Now, a variation or variant of the basic string method is due to the group of Benoit. So this is Benoit, and so we will assume. So we will use a Brownian description. We're going to use non-inertial Brownian dynamics to describe the evolution of the collective variable. And so what we do here is we consider a path C, which is a function of the collective variable connecting two basins of the free energy landscape, and we write the evolution of Z of alpha. And we're going to introduce here an average drift to evolve the string. We're not going to use just the gradient measure and use df perp. We're going to consider the average drift from an ensemble of unbiased trajectories, very short trajectories. And so what you see here are these different trajectories, and the green arrow is the average drift. And we're going to evolve the string following this drift. So the idea here is that the minimum action path is the property that the system initiating anywhere along the path connecting the two basins has the highest probability to evolve while remaining stuck along this path. Okay, and the condition of remaining along the path is met when the thermal noise that you can see here in the brown is equal to 0. Okay. So let me illustrate this in the very simple case that you've already seen of the alanine dipeptide, and we have the usual two minima, so the C7 equatorial, C7 axial, and C7 equatorial. I'm using here as a guess a very simple string connecting in a straight line the two minima, and I'm using, I think, like 20 images, 20 points, discretizing the path using 20 points in between. So how does it work in practice? So we prepare a configuration, we have P images, and then we generate an equilibrium trajectory with restraint, so that we restrain in our calibration, we restrain the position. actually the collective variables at the desired value along the string. And then from the equilibrium trajectory, now we remove the restraints and we generate an ensemble of short trajectories. We do that at every image along the string, right? And from this trajectories at each image, we infer the average displacement. We infer the drift. And then we parameterize the string to ensure, that's very important, we have parameterized the string to ensure that the images are equidistant in the collective variable space. And this reparameterization, so you can have like pathological situation like this, and you don't want that. You really want your images to be equidistant to prevent that the string is under-resolved in some regions of the free energy landscape. So this is an example of the nitrogen regulatory protein C, and we built the string, and from this string we've calculated the potential of reinforce, and of course the committer analysis that I presented before, and we see that at the top of the barrier we have indeed an isocommitter. Going back to the dialanine, so I'm starting with this reaction pathway, which is non-physical. You can see that we're going through a high free energy maximum. This is not a minimum action path, so we're going to involve the string, and we're going to use this algorithm in the tutorial. So you can see that. So what you see here, each snapshot of the movie is actually one iteration. At each iteration, I'm spawning multiple trajectories at each image. I'm calculating the drift. I'm reparameterizing the string until I'm getting this. Okay? At each step of the way, each iteration. So yes.
I can ask later.
Yes.
So you calculate the drift for each image along the string, and then you minimize the net drift for the next iteration?
Exactly. Okay, so this is the general strategy that you can follow. So you have like a new problem, you're interested. So imagine that you have, luckily, experiment gives you like two alternate states for a protein or enzyme, membrane protein, and you're interested in the transition between state A and state B. So you have these two states. You can start before running the string calculation, which can be pretty expensive. You can start with a model of, in the case of dialanine, I just drew a line, and it was just like a linear combination of the fighting side angle along the string, along that line. But you can use, as is the case here, you can use an elastic network model as a starting point. You can also use targeted MD, so targeted MD is basically going from state A to state B, minimizing or restraining towards the RMSD of the alternate structure, and then you can use a more elaborate transition path and scheme like the string method to optimize the string based on this rough guess reaction pathway. And once you have that, then you can calculate the free energy. Now I'm going to quickly, in the 5 next minutes, and I'll get it, I will stop. I'm going to show you how to derive the free energy along the string. So one approach is due to the group of Michele Parinello. This is the so-called path collective variable scheme. This is what we're going to use in the tutorial. This is not the only method. There is another method that I will mention, which is due to Attila Szabo. In the path collective variables, we have these two variables, which you can see as can be seen as basically the string itself. So we're going from image to image, from A to B, right? But to prevent sampling from drifting away from the string, which can happen, we're going to add this extra variable here, zeta, which you can see has a tube that kind of encompasses or embraces the sampling. So sampling doesn't drift too far away from the string. Okay, so what you have here is the continuous description. What we will use in our case is a discretized description. So it's discretized over the images of the string. So we have a weighted sum here of mean square displacements. So basically what you calculate here is at each time step of the simulation, you're calculating wherever you are along the string, you're calculating the MSD with respect to all the other images. Thanks to Giacomo Fiorin and Jerome Hennen, the author of Colvar, this calculation can be done pretty fast because we're ignoring, depending where we are on the string, it makes no sense. So if we are like at the image 19 of a 20 image string, it makes no sense to calculate the contribution with image 1. It's just too far from image 1. So it kind of dynamically optimized the number of the neighbors to calculate this weighted sum. So what you can see here is the representation of the previous fringy landscape, but this time in the S zeta landscape. Okay. And so this is the kind of this is the kind of string that we obtained for dialanine, and from that we can get the free energy change. So in this case, I've discretized further the string. I'm only considering this 5 points for my free energy calculation. So I'm just calculating the free energy based on these 5 points, but you can use the entire string, and especially now that it's becoming so cheap to calculate the free energy with collective variable. Incidentally, that collective variable is available in Colvar as a scripted function. And so because it's a scripted function, we don't have a Jacobian, we have to use the extended Lagrangian formalism. The other, by the way, so you can see that the free energy profile is very different. I mean, the shape of the free energy profile is very different from the gray one. The gray one was obtained by calculating a difference of RMSDs. So in this case, the reaction coordinate model is a difference of RMSD. So the RMSD of the current structure with respect to state A minus the RMSD of the current structure with respect to state B. Okay, so I'm navigating between A and B through the RMSDs. It's interesting to note that the shapes are very different. But as I was saying before, by virtue of the fact that free energy is a state function, the free energy difference between the two states is the same. Okay. And incidentally, if you take the two-dimensional map from a real two-dimensional free energy calculation and you integrate over the bases, you also get the same free energy. This is kind of safety check. The other approach that I wanted to mention, but I'm sorry, I don't really have time. This is Attila Szabo. This is more like a perturbative approach. This was used by Abhishek in application, the string method, free energy calculation along the string methods for ATPAs. I invite you to look at it. And I think I will stop here. Okay. Sorry for the application. Maybe some other time. Thank you. So we will.